You can do that, yeah. So for the collagen 6 disorders, we need to, I think, understand just a little bit so that we have a common ground to understand what collagen 6 disorders may be doing to the muscle. Secondarily, what the genetics behind collagen 6 disorders is. And thirdly, what that means for our treatment approaches, because collagen 6 is unique in all of these aspects from some of the other congenital muscular dystrophies. One of the challenges we face in any muscle disease, independent of collagen 6, is the organ, quote unquote, that we have to treat, is the entire muscle system of the body. So it's not just a kidney, nothing against nephrologists, but it's not just the heart. It is really a large organ. Skeletal muscle is the largest organ in the body. Depending on your level of fitness, it's about 40 to 50% of your body weight. So some people, that doesn't quite add up, but and it's 650 individual muscles in the body that one has to treat. So you have to think systemically. If you want to treat this disorder, you have to capture the entire muscle system for that. So that's a challenge that we always have to have in mind because there's a lot of talk out there of injecting stem cells into single muscles and so on that may help for a single muscle, but really our goal is to make all muscles that are deficient in collagen 6 better. So the other thing that is important to figure out is where is this actually playing out in the muscle system. And so let me just draw you a simple diagram here. So we have a bone up here. Whoop. And that's the bone. Here's a tendon. And then there is a muscle and another tendon. So what you need to move properly is you need to contract your muscle, obviously, to generate the force, but then you need to transmit the force through the tendon to the muscle. And so that's all needed for the musculoskeletal system to be functional and healthy. Now, collagen 6 is unique in neuromuscular disease in that it actually is not made by the muscle itself. Collagen 6 is made by connective tissue cells that are living in between muscle cells. And we call them the fibroblasts of the tissue. And the fibroblasts, their main job is to generate an extracellular matrix. And an extracellular matrix is what is around a cell. So if this is now a cell, a muscle cell, this will be the inside of the cell. And then there is something that coats every muscle cell from the outside, really hugs every muscle cell. And that's the extracellular matrix. So that's the muscle's connection to the outside world. And that goes all the way down to the tendon as well. So the tendon is mostly made of extracellular matrix. And that's where collagen 6 is. So collagen 6 is in the extracellular matrix here. And it is produced by the producers of extracellular matrix, the fibroblasts. It gets put out by the fibroblasts and then hugs up to the muscle, connects to the muscle. It's not made by the muscle, but the muscle seems to somehow need it. And it's also made in the tendons to generate extracellular matrix of the tendon. So as a result of that, we have a disease that not only affects muscle, but also affects other tissues with an important extracellular matrix. And perhaps most importantly, also tendon. Most of you have experienced the problems with tendons, the hyperlaxity of some of the joints, but also the contractures, these nasty contractures that are happening. So that's another aspect of this disease that's unique. So why does muscle need to have a matrix around it? And that's one of the questions that is still not fully answered. So one thing that the muscle needs around it, of course, is a matrix to be able to transmit force, right? So if the muscle was contracting and nothing is around it, it could just kind of flop there and no force would ever be transmitted. So it needs a matrix to transmit the force to the tendon, to the bone, for us to move. One thing. The second thing that a matrix really does for a cell, it makes the cell feel at home, healthy. In that, so every cell in the body wants to experience an environment around it that it knows, that it feels normal in. You can imagine that is actually very, very important. If you think about a cancer, like a cancer that grows and throws off little metastases. The body actually wants these metastases then when they go to other places to not feel at home. They want it to feel, you have left your neighborhood, you have left your environment, you better shut down. Yeah, you're not surviving. So this dependency of cell health to its normal matrix is essential to human biology. But if your matrix is abnormal because you have a genetic change in it, that could affect the cell in its own neighborhood. And we think that's what happens in collagen VI disorders. The cells now, without the normal matrix connection, are no longer able to support their own cellular health. They switch on pathways that are there, inborn in every cell, but they're not supposed to be active in this normal environment. But they seem to be inappropriately active in these cells. That is the basis of omega pill function. Omega pill is meant to make the cell more resistant against this now unnatural drive to shut itself down because the matrix isn't normal. So those are the downstream effects on muscle that, so these are all the mechanisms in muscle that happen as a result of the abnormal matrix, and this anti-apoptosis omega pill treatment is one of these effects that treats the downstream effect on muscle. Very, very important, and will always be important to treat the effect of the abnormal matrix on muscle. But if you do that, you are not treating the cause of disease, obviously. The cause of the disease is the mutation in the collagen VI. So even though all of this is very, very important, and we really need to do that and will always be important, if we want to move closer to the Holy Grail, if you will, you have to move closer to the mutation. Okay, so that's where it gets complicated. Because collagen VI, as most of you know, is not one gene, it's 3 genes. So we have called 6 alpha 1, alpha 2, and alpha 3. So all of these are made by different genes. These are 2 small genes, and this is a large gene. And these are sitting right next to each other on one of the chromosomes. This sits on a different chromosome. But what the cell does, it takes all 3 and makes collagen VI sequentially in a very complicated fashion. So it takes 3 genes, makes 1 building block, puts them together to 2 building blocks, puts them together to 4 building blocks, and that then is sent out to meet the muscle into the matrix. This all happens in fibroblasts. So you have these 3 genes that are involved in making collagen VI that shows up in the matrix. So does everyone in the room know their mutation or in the family mutation in the family? Everyone knows it? You don't?
No, we do.
You do. Anyone who doesn't know the mutation in collagen VI? We don't know. Okay, we talk. Because that becomes essential to know as we think about treatments for this. It becomes essential because there is 2 genetic mechanisms that can happen in collagen VI mutations, fundamentally different genetic mechanisms that lead to the same disease of collagen VI myopathies. By the way, stop me at any point if something like this, something doesn't sound right to you or you don't understand it. So these mechanisms are called recessive, and dominant. So what do I mean by that? So recessive means you need 2 mutations to get the disease. As you know, everyone has 2 copies of each gene because you inherit one from each parent. So you always have a double dose of your gene, 2 copies. Now in recessive disease, one parent may be carrying a mutation as a carrier who's asymptomatic because the normal gene copy is still there and allows for good health. And the same for the mother. But with a chance of 1 in 25, a child may inherit both mutated copy from each parent. So the child has no backup. Both copies are mutated. As a result of that, the protein is most of the time simply not there. It's gone. It's a loss of function. It's not there. So this happens like this. These are the mutations. Here's your parents, mom and dad. And so some children may have also carrier, some may be normal. But with a certain chance, a child will have inherited both copies of this. And so this child will now be lacking collagen 6. No collagen 6 there. The effect on the muscle is the same. The muscle has an abnormal matrix around it. It's missing its contact to collagen 6. It acts up. It is unhealthy. It gets this muscle disease, apoptosis and necrosis. So loss of function. Why is that important? Because in a loss of function, when a protein is simply missing, the idea, very simple-minded, the idea is, well, I'm going to replace the protein. I'm just going to put a good copy in. And that is the concept of gene therapy as it is most commonly understood. So you basically take a virus, a gutted virus envelope, mostly AAV, which is a naturally occurring virus that is basically gutted of all of its replicating and pathogenic and infectious elements. And by the way, this is mostly asymptomatic, even if we get infected by it. But you use it as an envelope, as a cargo carrier, and you put in a copy of your gene that's driven by certain mechanisms so it can be read. And what you do is you inject it in the bloodstream. It infects, hopefully, the fibroblasts in the muscle would be the idea, or the muscle. And then the coat would just disintegrate. The gene, replacement gene that's in there would be delivered to the cell. It would be hanging out in the cell and making the protein that's lacking. So that's very kind of simple-minded, but we're now entering an era where this actually reaches a stage where it seems to be actually working. So that's great. So here are the problems, though. First of all, you need to have a recessive mutation, so you need to have loss of function. You need to have a loss of function, and you need to have something that actually fits into the virus. And here is the problem. This cargo package here, as it currently stands, and that may change over time, but this cargo has a carrying limit. So there's certain genes that are too big to package into that. And if you remember the collagen 6 genes, so this one is about 3,000 plus base pairs. This is about 3,000 plus base pairs. This is, what did I calculate here? This is 9,500 base pairs. So these two fit into AAV as we currently use it, and this one doesn't. So for gene therapy, for a collagen 6 to work, you have to have two requirements. You have to have recessive mutations, loss of function, in one of these two genes. That's when you can think about gene therapy in collagen 6. So, and that is being tried now. It's being tried in mouse models of the alpha-2, where that is missing, so that proof of principle will be available. But unfortunately, this is only the minority of patients. Because most patients with collagen 6 disorders, some do, most patients with collagen 6 disorders do not have recessive mutations in one of these two genes. Most patients with collagen 6 disorders actually have something that's called dominant mutations. So let's look at dominant mutations. Now in a dominant mutation, you only need one mutation to cause a problem. So here, there would be one mutation, and that mutation alone is sufficient to cause a problem with the collagen 6. And I'll explain to you in a second why that is. So in a family, that usually means that either you have an affected parent as well, so that it is inherited from generation to generation in a 50 to 50% chance. Or more commonly in our world here in more pediatric diseases, both parents would be normal. They wouldn't carry a mutation, and this mutation would be de novo, a new mutation. Sometimes, in some parents, only a subpopulation of the cells have the mutation. We call that mosaic. That gets a little tricky. So then the parent is quite a bit milder than the child is, because the mutation is diluted out between new and between mutated and normal cells. But most of the time, it's a de novo mutation in the child. Or if it's a milder disease, there's a direct inheritance from the parent to the child. So why is this mutation alone sufficient to cause a problem then? That's the question, right? We have mutations that are loss of function, and I should say these mutations here that are causing absence of the protein. If you're a carrier for a mutation that causes absence of the protein, you have 50% of the protein left, right? Because you're carrying a mutation that abolishes collagen 6. 50% of collagen 6 is fine. You have no phenotype. If you're a carrier for a loss of function with just 50% normal collagen 6 hanging around, that's normal. That's not a phenotype. That's not a clinical problem. So why are these then causing a problem if you have only one copy of the two copies affected? The reason for that is something that we call dominant negative. So this is dominant negative. So what this mutation does, where's my little diagram here? So this mutation now, let's put it in this gene here, perhaps, right here it is. That mutation gets carried forward. It doesn't knock out the gene. It doesn't allow for no protein being made. It's actually able to sneak itself in. It's sneaky mutation. It sneaks itself into the assembly process of collagen 6, all the way down to the final product. And so it is not recognized by the cell as a mutation and discarded. It is built into the collagen 6. And while it's being built into the collagen 6, it messes up the collagen 6. So it acts basically in a toxic way, taking down all the normal collagen 6 that the cell is trying to make. It really toxifies the product. And that's why it's so nasty, so dominant negative. And as an end product, most of this final product here will have a mutation on board. Only very few of these final product collagen 6 will be completely normal. Not enough to prevent disease. So that raises the question, how do I go about this? And the answer is really, we know that parents who carry an abnormal collagen 6 copy that makes no protein, that's completely missing, so they have only 50%, but the 50% that they have is completely normal. Those parents are normal. So if I were to find a method to knock out this mutant copy of the gene, just take it out of the picture, get rid of it, so that I have only one normal copy left, then I would be able to make 50% normal collagen, and I would get rid of the phenotype. So you're basically, why are you waving at me? Oh. So what do you...
Hello.
What is it?
From Rachel. We're supposed to be eating lunch in here.
Okay.
So when you guys finish up, we'll come in for lunch.
Am I allowed to finish?
Yes.
Okay, thank you. So give me 5 more minutes, and then I finish up on that. So the concept is that of a mutation-specific knockdown. I want to develop something that goes after the mutation, knocks it out of the picture, takes it out so it can't mess up the normal collagen 6 that we have. Do you follow me with that? Yeah, great. So that actually works. So when you do that in the dish and you take fibroblasts from patients with collagen 6 disorders that make no collagen 6 because a mutant messes it all up. If you have a probe, so no collagen 6 is being made. If you have a probe and some sort of thing, some reagent that goes after this but doesn't go after this, takes this out, then a normal collagen 6 matrix can be made again. So the So that works in principle. It works in the dish. We are now also trying it in the mouse. So what are the problems? So the problems are this, not really problems, but the challenges, I would say. You have to have something that can be injected, that is safe, that is absolutely specific to the mutant here. And we have such agents. They're called oligonucleotides, oligos. You probably heard about these little pieces of modified genetic material that recognizes the readout from this directly. And they come in different flavors and different chemistries. But the principle of this as a drug is already out there. Several compounds that have similar chemical characteristics are already FDA approved for other conditions with other things and other goals in mind. But the drug class, if you will, is something that we've seen before getting actually through the approval process and working. So that's good. The challenge is you have to be mutation specific. So you have to design this for each mutation that you want to target. This is not an unsurmountable problem because this is really at the basis of precision medicine or designer medicine. That's really where we have to get to. And also, there are several mutations that occur more than once. There are common mutations that we can go after first and prove the proof of principle and then go after the rare ones as a designer approach. The advantage of using these little oligos is you're not doing permanent damage. This is reversible. You give it as long as it's working for you, but it doesn't mess up anything in the genome or anything else. So that's a good safety factor. The disadvantage is you have to keep giving it to maintain the effect. So there is, and with that I finish and take your questions, there is a new technology that you all heard about, which is gene editing, the CRISPR-Cas. So there you have an actual thing that actually cuts the mutant gene itself in the genome to cut it and inactivate that. And that is a potential therapy for these types of mutations as well. And again, we're trying that in the dish. But you can imagine the margin of error for this therapy is much smaller because these gene scissors, if you want them to cut, they're only supposed to cut that very spot in the genome, nowhere else, nowhere in other spots in the genome, not in the germline, nowhere else. And so that safety margin is still not explored, but it's not unique to our disorders. It's a problem across all genetic diseases where this is being considered. So everyone is working on moving that into a realm that is more safe. And that will be then, if you will, a permanent genetic fix in the cell that has it. So the oligos here, or whatever chemistry we decide is the best one for this, are the most likely to move forward for the more common mutations first. And then the gene editing part of it is a little bit more futuristic, but is also not out of the question for this at all. I'm sorry, this was some heavy genetics here and heavy molecular biology. But do you have, did you follow that? And if you have any questions, it would be a good time to ask. Yeah.
So the question I have is, based on specific diagnosis, is it always a specific mutation? Is it always either recessive or dominant, yes, or is it, can it vary?
Yeah, so it's, that's why it's so important to really understand your genetic testing report. So am I sitting right here? So because a pathogenic variant in collagen 6 does not, even if it's a pathogenic variant, it does not know automatically mean this is causing disease in you. For instance, if it's a recessive mutation, you may just be a carrier for that. However, if it's a dominant mutation, that's a disease-causing mutation in the person that was tested. So you have to understand each individual mutation in its effect, whether it's recessive or dominant. So that's a challenge of interpreting genetic testing in the collagen 6 genes. You really have to understand that. But we know the common dominantly acting mutations. We know what they look like. We know where they sit. So we're very good at predicting the dominant mutations to be dominantly active. And often we can prove that by showing that they're not present in the parents, that are de novo inherited, and no other one in the family carries them. Does that answer your question?
Maybe.
Follow up.
Well, so I guess I'm still trying to, so specifically with Ulrich's, or is it always caused by, but you're saying that can be caused by either the recessive or the dominant. So, okay, that's
And you have to always be sure that you find that out, that you really bring it to the final conclusion, that you know, because otherwise you cannot even start thinking about these things. Yes, exactly. Eunice. Yeah, so it will be tried. So we have a knockout model of the alpha-2, and so does Valerie. So you have a fa- one is a have they both been tested or? Yeah, so usually you can go by clinical status. So if someone is unaffected in a dominant gene that's inherited in the family, it usually means the person is not carrying the gene. But you can easily test that very specifically because you know the mutation in the family. And so, you know, for peace of mind and family planning reasons, it's very easy to do and put that at rest. Yeah, and we have genetic counselors here in the room that can talk about that.
So I've been hearing about like these read-through like drugs that you have like a premature stop codon. Are those gene specific or do they work?
No, those are not necessarily gene specific. It's a good question. So some subset of mutations in the collagen VI genes are premature stop codons. And so for those you can try this drug class. The effect of this drug class is so far, not maybe whopping enough to make a visible difference. But the principle of this drug class is right. So if those drugs get further developed and become more and more powerful, then it would be not mutation specific. If you have a premature stop codon mutation in any of these genes, you could try that. Yeah. Yeah, sure. Final question? And then you can grab me at lunch.
Okay. First of all, I'm thrilled to hear all this. Thank you so much. You are our heroes. And then the second heroes are all the people affected by this, which are teaching us.
First heroes.
I wanted to say this. But I see a lot of variations in the symptoms of the disease. Is this related to the gene? To the mix of several genes, or how it varies?
Well, that's a really good question. So it's partly related to the mutation. So there are some mutations that are more consistently causing a severe phenotype, and some that are more consistently causing milder. But even within the same family, where you have maybe two affected children or two affected generations, the symptoms can vary. So there are modifiers of how the disease plays out in every individual and his or her respective genetic background. We would love to know those modifiers. It's a really good question. I think we have to wrap up.